So can you hear me? Reply. Yes, can you hear me? Yes, you have to reply. So let us start now. So in this lecture, I would like to discuss about the two component system. In previous online lecture, we have been discussed about the one component system. We have taken two examples of one component system, that is water system and sulfur system. So I would like to show to you the diagram belongs to the water system once again. Just you have to see the diagram for water system, phase diagram for water system. 1 minute. So this is the phase diagram for the water system. Okay. So with reference to the phase diagram, we have explained the number of the phases, the number of the areas, number of the curves, triple point, and we apply the phase rule to the one component system. Then we have taken the second example that is known to you, that is a sulfur system. So in sulfur system there are four phases are existing: rhombic sulfur, monoclinic sulfur, liquid sulfur, and vapor sulfur. So this is the diagram for the sulfur system. So as compared to water system, somewhat the diagram of the sulfur system is complicated but not difficult. Okay, so there are a number of areas are equal to 4, number of curves are equal to 6, number of triple points are equal to 4 in the sulfur system, and we apply the phase rule to the areas, to the curves, to the triple point. Okay, and we find out the degree of the freedom by applying the phase rule. Okay, so now let us going to discuss this two component system. Two component means number of components are equal to 2. So let us write here number of components equal to 2. C it is equal to 2 here. Okay. So for two component system, we have to change the phase rule, because the phase rule which is used by us in the one component system, that is F it is equal to C minus P plus 2. This phase rule cannot be used, because in case of the two component system, as C equal to 2, so if we put C equal to 2 here, so 2 plus 2 4, 4 minus P. So number of the degree of the freedom becomes equal to F it is equal to 4 minus P. Now suppose that if P equal to 4 phases are existing in equilibrium with each other, then the degree of the freedom F becomes equal to 0. But we know that at a time 4 phases are not in equilibrium with each other. Only the 3 phases are in equilibrium with each other, that is solid in equilibrium with liquid, it is in equilibrium with vapor at a time. So we cannot show 4 phases to be in equilibrium. So if it is not equal to 0, it means that the system is not non-variant or invariant. We cannot show this with the help of the phase rule F it is equal to C minus P plus 2. That is for the one component system, but in this case two component system we cannot use that phase rule. Okay, therefore it is necessary to study this condensed phase rule. So let us see what is this condensed phase rule. we are going to change the phase rule now here, and that phase rule, it is called as a condensed phase rule. Now the two component system have some general characteristics. The first general characteristics is that the composition of each phase can be expressed with minimum two components. We require minimum two components to express the composition of each phase. We require two components to express the composition of each phase. Okay. So suppose that if we consider the lead and silver system, for example, lead and silver system. So in this lead and silver system, the two components are lead and silver. Now to express the composition of each phase into the system, we require minimum two components. Okay. Now for two components C equal to 2, the phase rule is, okay, C minus P plus 2, already we have explained here. So it is equal to 4 minus P. The phase rule can be written as 4 minus P, F is equal to 4 minus P. Now when the system is invariant, that is F equal to 0, the maximum number of phases in equilibrium are equal to 4. 4 phases should be in equilibrium with each other, but generally in the phase diagram we have shown at the triple point the 3 phases are in equilibrium. So it is difficult to show the 4 phases are in equilibrium. Okay, that is not possible. Then when the system exists in a single phase, suppose that only one phase is existing. Where is only one phase is existing? In the areas. In the areas only one phase is existing. In the water system and in the sulfur system, we know in the areas only one phase is existing there. That is solid phase, liquid phase or vapor phase. So it means that when only one phase is existing, P it is equal to 1. Then if P it is equal to 1, then this phase rule F it is equal to 4 minus P. So P it is equal to 1 here. So it is 4 minus 1. It is equal to 3. It means that degree of the freedom becomes equal to 3. We have to consider, we have to take 3 degrees of the freedom. Then we can draw the diagram. Okay. So it means that in addition to pressure and temperature are the two variables. In case of the water system and in case of the sulfur system, we have plotted the graph, that is phase diagram. It is pressure versus temperature. Now in this case, if for a single phase the degree of the freedom will becomes equal to 3, so we have to take the third variable here, and that third variable, it is composition or concentration. Composition has to be taken into account. It means that we have to add the third variable. So in the phase diagram we have to represent 3 variables: pressure as well as temperature as well as composition. Means we have to change the 3 variables and we should have to study the system. So it is quite difficult one. So construction of the phase diagram of the two component system will require 3 coordinates. According to the phase rule, F is equal to 4 minus P. So we require 3 coordinates: pressure, temperature and concentration. 3 variables are required. Okay, so this will lead to 3-dimensional figures. How we can take the 3 variables? Not easily possible. So we have to draw the 3-dimensional figures, and which cannot be drawn conveniently. The 3-dimensional figures on a paper or on a blackboard, we cannot draw the 3-dimensional figures. We only draw the 2-dimensional figures. That is pressure versus temperature, pressure versus concentration, or temperature versus concentration. Such diagrams can be plotted. But at a time we cannot take the 3 variables, because it will require 3-dimensional figure and it becomes quite difficult. Hence, 2 coordinate diagrams are drawn by keeping the third variable constant. It means that in this system we have to keep the one variable constant. We cannot change it. Either pressure should be constant, temperature and concentration can be changes, or concentration can be constant, pressure and temperature can be changes, or pressure can be constant, temperature and composition can be changes. Okay, so we can take only two variables. So for two coordinate diagrams, the third variable should be constant. Now generally, if the measurements are made at constant pressure, if the measurements are made at constant pressure, one of the variable of the three get fixed. Generally, there is a less effect of the pressure onto the solids and liquids. The effect of the pressure, it is more and more onto the gaseous system. Okay, so if we keep the pressure constant, then the phase rule can be written as, you can see here, the phase rule can be written as, we have to change the phase rule now. The phase rule, it is F, it is equal to C minus P plus 2, but actually here 1 is taken. Okay, this plus 2, it is 1 for pressure and 1 for temperature, and if we keep the pressure constant, okay, so only one temperature can be changes there. Okay, so F, it is equal to C minus P plus 1. So in this two component system, C, it is equal to 2, so F, it is equal to 2 minus P plus 1, so it is equal to 3 minus P. So the phase rule can be written as F, it is equal to 3 minus P. And this phase rule, what is the initial phase rule? F, it is equal to 4 minus P. According to this, F, it is equal to C minus P plus 2. But in case of the two component system, we should have to suppose keep the pressure constant, because the effect of the pressure, it is more and more onto the vapors, but onto the solid and liquid, the effect of the pressure is generally very less. So we have to keep the pressure constant there. So this phase rule now can be changes. F, it is equal to C minus P plus 2, it can be changes here. So we can write that phase rule here. That phase rule can be written here. You can see that phase rule, it is F, it is equal to C minus P plus 1. So in place of this 2, we have to take 1 here. So we have to change the rule, and many times we are changing the rule. Okay, to achieve something, we have to change the rule. Okay, so F, it is equal to C minus P plus 1. So it is a two component system. So F, it is equal to 2 minus P plus 1, that is F, it is equal to 3 minus P. So this rule, it is called as a condensed phase rule. This is known as a condensed phase rule. And the system studied under this condition called as a condensed system. Okay, so we are going to study now the condensed system by changing the phase rule. So for two component system, we cannot use this phase rule now. F, it is equal to 4 minus P, because there are certain difficulties that is known to us. Okay, particularly when for areas there is only one phase. So F, it is equal to 4 minus 1, F, it is equal to 3 now here. 3 degrees of the freedom. So 3 variables we have to apply, pressure, temperature and concentration. But we cannot draw the diagram with the help of the 3 variables. That is a 3-dimensional diagram. Okay, so we have to keep one of the variable constant, better way. Then the phase rule can be written as F, it is equal to 3 minus P. Then we can draw the phase diagram. So now you can see here, for one phase system, particularly in the areas, there is only one phase. So it is 3 minus 1. So degree of the freedom F, it is equal to 2. So we can see the effect of the two variables, that is pressure, temperature, concentration, like that. So we can change the two variables and we can draw the diagram. That's why condensed phase rule is applicable for two component system. So we have changed here the rule, and the new rule, it is called as a condensed phase rule. Now let us apply this condensed phase rule for the system, two component system. So application of phase rule to two component system. By taking the example now, I would like to explain this. Application of phase rule to two component system. Remember, in case of the two component system, C becomes always equal to 2. Okay, C becomes always equal to 2. Now the example of the system, it is eutectic system. Okay, eutectic, and the example, it is lead silver system. Lead and silver. Lead is a metal and silver is also metal. lead silver system. Okay, two components are existing there, lead and silver. These are the two components, purely solid. Lead is solid, silver is solid. Consider two components such as lead and silver, which neither combine to produce a compound nor form a solid solution. When we are mixing these two metals, they neither combine to produce the compound. Okay, they neither produce they neither combine to produce a compound nor form a solid solution by dissolving in each other in the solid state. It means that they are not going to combine. These two solids are showing their different identity. They never combine. Even though we are trying to mix up them, but generally they are not going to combine. Okay, so there is no any solution is formed by dissolving in each other in the solid state. The components are completely miscible with one another in the liquid state. When we are melting them and converted into the liquid state, they are completely miscible. Then we cannot identify which is silver, which is lead. Okay, but in the solid state, these two solids are separate. They are separate, two phases are existing. Lead is separate phase, silver is separate phase. Colors are also different. All of you know silver color, lead color. It is a grey like color. Silver color. It is silver shining. All of us know. Bright shining. So both are showing the different identity here. Identity. Now on solidification, they give rise to an intimate mixture. Suppose that liquid is converted to solid. They give rise to an intimate mixture that is known as a eutectic mixture. Suppose that if we have taken the lead silver liquid mixture, completely miscible, and we are doing the solidification process, then what happens? Lead and silver can be separated from each other, and they give rise to an intimate mixture known as a eutectic mixture. Okay, let us see. It can be studied with the help of the phase diagram. So it is necessary to study the phase diagram of such a system. So you can see this phase diagram now. Let us see. Because with the help of the phase diagram, we can understand so many things. So this is a lead silver system. Okay. Phase diagram is so simple. Let us see here. 100% lead is here on the left hand side. 100% silver is here on the right hand side. On the left hand side, 0% silver. Okay. So 600 Kelvin, it is the melting point of the lead. 600 Kelvin, it is the melting point of the lead. This is the phase diagram, temperature versus composition. Pressure is constant here. Temperature against composition or concentration. Better way, composition. So lead and silver is existing. So onto the extreme left side here, 100% lead we have taken and 0% silver. So whenever there is a no silver, the melting point of the lead, it is 600 Kelvin, very high temperature. Onto the right hand side you can see 100% silver, 0% lead. Melting point of the silver, it is 1234. Whenever there is a no lead. Whenever there is a no lead here, 0% lead, then the pure silver shows the melting point 1234 Kelvin. But now as we are moving from this side to this side, okay, the percentage of lead goes on decreasing and percentage of silver goes on increasing. Okay, as we move from LHS to RHS, percentage of this lead goes on decreasing and percentage of this silver goes on increasing. Okay, so let us explain now this diagram. Now this is the area of the liquid melt. Both lead and silver are in the liquid state completely miscible to each other. Now you can see this point here. Take this point. What is the temperature corresponding to this point? Very low temperature here. Suppose that it is around 580 Kelvin. This is 580 Kelvin. Okay. Now this is the point where this is the area where both lead and silver are exist into the liquid state. So in presence of lead or in presence of silver, they are melting, their temperature will be different. Okay, they are totally into the liquid state. Actually, pure silver will be liquid at the 1234 Kelvin, and pure lead will be in the liquid state at the temperature of 600 Kelvin. But if you see here, whenever there is a 2.6% of silver and 97.4% lead, so in presence of the silver or in presence of the lead, their melting points, they are in the liquid state totally here. Okay, so their melting points are supposed to be less here. It means that as we change the composition of the system, the melting point of the lead and silver is also going to be changed. Okay, as we change the composition of the system. All of you aware about the melting point. Generally in practicals we have taken the melting point. Generally the pure substance has given the correct melting point, accurate melting point. Pure substance has given the accurate melting point. But if there is certain impurity is present into that, the melting point of that pure substance will be affected. It will be either less or either greater. Because in presence of the foreign substance, it means composition will be changed. And as the composition will be changed, the melting point of that substance is also changing. So in this case also, in presence of lead or in presence of the silver, the melting point will be changes here. Let us explain this diagram now. So we understand that the melting point of the pure lead, it is 600 Kelvin, and melting point of the pure silver, it is 1234 Kelvin. And along this x-axis, we are going to change the composition here. So let us see the explanation. The two curves AC and BC intersects at the point C here, called the eutectic point. Let us see here. The two curves AC and the curve BC meet at the point C. And this point C, it is called as a eutectic point. Okay. Along this curve AC, the two phases are existing. Okay. Along this curve AC, the two phases are existing. There is a lead as well as a liquid melt which containing the silver along the curve AC. And along the curve BC, there is a liquid plus solid silver along this curve BC. And at the eutectic point C, this is the point where the three phases are existing. Which are three phases? The liquid melt is there, the solid lead is there, the solid silver is there. Okay, so at this point, therefore this point C, it is also called as a eutectic point because three phases are existing there. So see here, point C is called as a eutectic point. At point C, three phases, solid lead, solid silver and liquid are in equilibrium here. You can see here, solid lead is here, solid silver is here, and this liquid, they are in equilibrium. Okay, so three phases are existing at this eutectic point C, where the composition of the eutectic mixture, it is at this point C, 2.6% of silver is there and 97.4% of the lead is there. Okay, and corresponding temperature is 576 Kelvin. So this temperature, it is also called as a eutectic temperature, 576 Kelvin. At this 576 Kelvin, the three phases are existing here, and composition corresponding to this, it is 2.6% of silver and 97.4% of the lead is there. When this composition is there, if there is any change in the composition, then the system will be totally changed. Okay, so try to understand this. Let us see now. So applying the reduced phase rule to this, F is equal to C minus P plus 1 or F is equal to 3 minus P. So at the eutectic point, there is three phases are existing. So P is equal to 3. So 2 minus 3 plus 1. So it is F is equal to 0. So the degree of the freedom becomes equal to 0 here. And we know that is also called as a triple point because three phases are existing here. This eutectic point, because there is a formation of the intimate mixture. Eutectic means, what is the meaning of the eutectic? Easy melting. It is a Greek word. The meaning of the eutectic, it is easy melting. Okay. So if we change the composition, if we increase the temperature here little bit above 576 Kelvin, then totally only one phase is there, that is a liquid phase. But when the temperature it is 576, the composition it is eutectic composition, 2.6% silver and 97.4% lead is there. Okay, so the F is equal to 0 here at the eutectic point, means the degree of the freedom becomes F equal to 0. The system is called as invariant system or non-variant system. F is equal to 0 because it that will be existing only at the fixed temperature and fixed composition. If you change it, if you change the temperature, the system will be changes. If we change the composition, the system will be changes. We cannot change it. It should be fixed. It should be constant. Then and then that eutectic point will be seen in the phase diagram. That eutectic mixture will be seen in the phase diagram. So at this eutectic point, Cf equal to 0, the three phases are existing there. Okay. Thus at point C, the system is non-variant. This is known to us. It can exist only at a definite temperature and composition of the liquid. The temperature of the eutectic, it is 576 Kelvin and the composition is known to us 2.6% silver and 97.4% of the lead. Okay, so this is very interesting now. At this temperature, the three phases are existing. The liquid melt as well as solid silver and solid lead. The point C represents the lowest temperature at which lead and silver can exist in equilibrium with the liquid. This is the lowest temperature. Okay, lowest temperature at which the three phases are existing with equilibrium with solid silver and solid lead in equilibrium with the liquid melt. That is also very interesting one here. The temperature 576 Kelvin corresponding to the eutectic point C is called the eutectic temperature, that is known to us, and the composition 2.6% silver and 97.4% lead corresponding to the eutectic point C is called as eutectic composition. So what is a eutectic composition? 2.6% silver and 97.4% lead, and the corresponding temperature that is 576 Kelvin, and that temperature it is called as a eutectic temperature. Okay, so the another explanation is that the two curves AC and BC, along this curve BC, the two phases are existing here. P equal to 2. Okay, P equal to 2 here. We can apply the phase rule to this also. We can apply the phase rule along this curve BC. Two phases are existing. So let us see here, along this curve BC, the two phases are existing. F is equal to 3 minus P, that is the condensed phase rule. Two phases are there. So F is equal to 3 minus 2. So degree of the freedom becomes equal to 1. So you can see here at this composition, there is only one temperature corresponding to this. F is equal to 1 here. Okay. Similarly, here along the AC, the composition will be solid lead. It is in equilibrium with the liquid melt here. Okay. So we are going to decrease the temperature here along the curve AC. Similarly, here along the curve BC, the temperature goes down. Okay. So along this curve AC or BC, the two phases are existing there. F is equal to 1, degree of the freedom F is equal to 1. The system is called as a monovariant or univariant. Now this principle can be used in the desilverization of the lead. This method can be used in the desilverization of the lead. To remove the silver from the lead, this method can be used. Particularly in the alloy, some quantity, trace quantity of the silver is there, then this method can be used. The mixture can be heated and later on it is cooled, then the separation will be takes place there. So let us see that process. It is called as a desilverization of the lead. Okay, so what is the desilverization of the lead? Desilverization means to remove the silver from the lead, to separate the silver from the lead. Okay, so to obtain the pure lead here, you can see the process, it is called as Pattinson's process of desilverization. So in this case what happens? First of all, we have to take the argentiferous lead. Argentiferous means it will containing argenti means silver. Argentiferous lead containing a small percentage of the silver is first heated to temperature above 600 Kelvin. We have to heat the mixture above 600 Kelvin. Okay, it is then allowed to cool. Later on we have to cool. That mixture should be cool. The temperature will fall along the line AB. You can see here that process, it is shown here. Okay, above the temperature 600 Kelvin, we have to heat the mixture. Means it is totally converted into the liquid state. Means lead is maximum there, no doubt. Trace quantity of the silver is there and we want to remove the silver. And that process, it is called as desilverization process. So at this point A, we are going to up to B. We are going to decrease the temperature. So when the point B is reaches there, the lead gets separate outs. The lead gets separate outs here, and silver will be in the liquid melt. Silver will be in the liquid melt. So you can see here. Okay. It is then allowed to cool. The temperature will fall along the line AB. We are going to decrease the temperature here along the line AB. When the point B is reached, lead will crystallize out. When this point B is reached, lead will crystallize out. Means lead is going to separate. And the solution will contain the silver there. Okay. The solution contain the silver there. So cooling is continued. That process, it is going on. Cooling is continued when lead continues to separate out, because we are decreasing the temperature and we know that composition of the lead is greater there. So lead will be going to be separate out, which is constantly removed. The liquid melt grows richer in silver. That liquid melt will consist of the silver. You can see along this BC, that liquid melt richer in the silver. And when the point C will be reaches there, the silver composition, it is 2.6% silver, and lead composition, it is 97.4% of the lead. In this way, lead gets separated from the silver. The lead gets separated from the silver. Okay, which is constantly removed. The liquid melt grows richer in the silver, and till up to the eutectic composition, 2.6% of the silver is reached out. Okay. Thus, the enrichment of the silver from the very low concentration to about 2.6% is possible by this process. Particularly, this process can be used for desilverization of the lead. To remove the silver metal from the lead, we can obtain the pure lead. Silver can be separated out. Okay, so this is the two component system, that is a lead silver system. Once again, you have to see this diagram here and understand this diagram. The curve AC, it is the melting point curve for the lead. Curve BC, it is the melting point curve for the silver, because we are going to decrease the temperature there along the BC, and along the AC also the temperature is going to fall. And the liquid melt, totally this is where only one phase is existing here. Along the curve, two phases are existing. And at the point C, that is the eutectic point, this point C is very, very important here. Okay, you can see here eutectic plus solid lead, and on this side eutectic plus solid silver. Silver is going to be increasing here. So this is the phase diagram for the two component system, and we can use here the condensed phase rule, because this is the diagram of temperature versus composition. We are going to change the composition, and temperature is also going to be changed. Okay, so this is the lead silver system, very important system. Particularly this system can be used for the separation of the silver, can be used for the separation of the silver from the lead. Okay. So thus today we have discussed the two component system for lead silver system. So I would like to end the lecture now. We used here the uh, two component system. Okay, we used here the two component system. C it is equal to 2. Okay, so I would like to end the lecture now.